particles behaving as waves, and that's really where the problem solving for today is going to be, is chapter 39, and chapter 44 is just for the fun of it. It's just a very light introduction to particle physics. Very light.
Solving particles.
No.
So that way we know what's going on when they go, hey, we're turning on the hadron again.
Yes, you will. Well, you will know a smidgen of what's going on.
Words that I know.
There you go.
I just want to know, can they really create a black hole that's so
Yes. No, they cannot.
Okay, I think so.
And physicists also have a very dark sense of humor. So anything that sounds like it's going to end the world is probably some physicist laughing, like,
We're totally going to do this.
CNN picked that one up.
Or they finally snapped and they do want that.
Or that.
Okay, semi-related tangent.
Yeah?
The show The Flash, I don't know if anybody watched it. They used a hadron-style colander to shoot an atom at the Flash so he could travel back in time. Can they do that?
Hey, you're spoiling the very end. I haven't watched it.
I should say that was 4 weeks ago, though.
Just put them in a particle.
Let's just say television is very entertaining. We'll just leave it at that.
Television physics?
Television is very entertaining.
I would think that. I can tell you totally.
Where are we at from time? I don't want to. Okay. Okay, so these are just the slides from last week. So you probably heard me talking a little bit about this, so I'll keep this brief. So last week when we talked about revisiting diffraction, we said if you sent one photon of light through that single slit, you'd still end up with a diffraction pattern because that photon acts like a wave, and as it passes through the slit, the wave interferes and you get a diffraction pattern. So with the double slit, you've got two slits to go through. Just like with a diffraction experiment, if you decrease it to 1 photon per minute passing through 2 slits, you get an interference pattern. Remember, interference is where you have 2 waves of light coming through those slits. They interfere with each other, 2 waves interfering with each other. That's what you get, is an interference pattern on the screen. So when you send 1 photon through 2 slits, you get an interference pattern. Yes, I'm trying to emphasize what's happening because that's weird. It's weird, right? If you try to observe which slit the photon went through, so you put a little detector to say if a photon passes through this slit, record it on the computer. The detector is going to affect the results. I mean, because how is the detector going to work? It's probably a laser beam, right? It's light. If a photon, it's inherently going to be affected by the laser. Yeah, so if you treat it like a particle and you ask which slit it goes through, it will act like a particle and it will create just the pattern of the slits on the other side. It no longer interferes with itself. So if you treat a photon like a particle, it behaves like a particle. If you say this is a black box, I'm not gonna look, I promise I won't look, then it behaves like a wave.
Is that discovered theoretically, or did someone actually do that?
Oh, it's you can do this.
Someone shot 1 photon?
Oh yeah. Yeah. The picture, does your book have a picture of this one? I'm sad I don't have a picture on my slide, but I feel like this is. Yes, this is where there's many aspects of this lecture.
Oh yeah, back in the day.
So this also reminds me of Feynman's experiment. So Richard Feynman, his PhD thesis, he was discovering a lot of particles and their antiparticle equivalents. So there's the electron and a positron. And so a positron has like all the reverse properties of an electron in many ways. So if an electron is spin up, then its positron will be spin down. Like a lot of the reverse properties. Well, the other weird thing about an electron that he predicted was if you generate an electron, so there's certain kinds of particle collisions where you'll generate an electron. Some kind of particles will collide and it creates an electron. he said during that collision, you not only are creating an electron, you're creating a positron at the same time. And as an electron goes forward in time, a positron is going to go backwards in time. And so the moment that you fire off your particle to create the collision, if you have a detector there, it will detect the positron before the collision has occurred, because the positron is moving backwards in time. Now let's say you've got a button, and every time you push the button, it's a random number generator of ones and zeros. And it may or may not fire that beam to create the collision. But it knows the moment the button's pushed whether that's going to be a 1 or a 0. And so the computer knows that, and it'll detect the positron even before the collision has occurred, even if you've got the random number generator in there. And so then if they've even done this experiment where they put electrodes on the brain of the scientist, and they said, you get to choose. So we're going to put in free will here, right? You get to choose whether you push that button or not. And before you've even hit the button, it detects the positron.
What?
Because the universe knows your choice. Because you don't really have a choice. You think you have a choice, but you don't. This is real. This is factual. Yes, this is actually real.
Like the theory of freedom in America.
You should be able to change your decision.
Yeah.
Is there an explanation for why one photon, or how one photon interferes with itself?
Yes. So, and this we'll get into later today, but really, really small particles, and this applies to electrons too, but photons even more so. Photons have no mass, and so it's really easy to make this leap in your brain to say, you know, the photon isn't really a distinct particle. It's a probability of that particle existing at that given location in that given point in time. And so to describe a photon, we actually use a wave function. It's a probability function. And so it has a higher probability of existing where you think it's supposed to be, but it also has a probability of existing anywhere in the universe. So it's literally, it has an equal probability. This is kind of bridging between math and philosophy and physics, but it has an equal probability of going through both slits, statistically. So it does. So yeah, so I mean, if that's hurting your brain because we're thinking about it like a particle, if you think of it like a wave, and we know that a wave, when it intersects those two slits, it branches into two waves, and the two waves interfere. So if you just remember that photons are waves, they are electromagnetic waves. We looked at the wave-like properties of the electric field and magnetic field. It has wave properties. And just accept that when we want it to act like a wave, it acts like a wave. When we want it to act like a particle, it will act like a particle. And we really have no choice. Okay, so here's another fun one, Schrodinger's cat. So this is another thought experiment that's very much related to what we're talking to. This thought experiment, if you've never heard it before, you have a box, right?
Okay.
You have a cat, because every scientist needs to have a cat. You put your cat in the box, all right, and then you've got a device inside the box that will release a gas that will kill the cat, but there's a release mechanism that's tied to a random number generator. So you push the button on the outside, that's going to go through the random number generator. 1, it kills the cat. 0, it doesn't kill the cat. But you don't know what actually happened. You just push the button. You've got a 50-50 chance that you killed the cat. You don't know until you open the box whether your cat is dead or alive. So what is the cat when the box is closed? Is it dead or is it alive?
Superposition of both.
It's both. Yes, it's both.
Of course, but
One of those backwards time
the
travel
photon, yeah,
positron.
first knows the cat's dead.
There's one way to settle this. We have a cat, we can have a lab 5.
Lab 5.
Sounds like one of those Zen koans.
Yes, it is, yes.
Sound is one in.
What's one sound? Yes, that's how I feel about much of this.
Right here.
If you,
That's what it is.
if you let it go and just accept that this is bridging between physics and philosophy and just say, you know, this is kind of cool. It's weird, but it's kind of cool, so. And can you guys see this lovely picture of the cat that says, suck it, Schrodinger?
Shoot through the box.
I love Google image shirts. I just have to search for Schrodinger's cat.
There was another one that had like the stereotypical cartoon guy standing there, and he pushed and just pushed the button, and he goes, "What?" He makes a check mark next to the guy's name.
Oh,
Like, did he kill a cat or not? Check.
creepy.
Pretty funny.
Whoop. Oh, okay. So, any questions about that weirdness? Don't worry, there's more weirdness to come.
I love weird.
Yay for weird.
Yeah. We're okay. We're okay on the weirdness for now? Okay. Now we're going to talk about something weirder. Particles behaving like waves. So if you thought photons behaving like waves was weird. So de Broglie was a guy who came up with the hypothesis. And we've used this term before, wave-particle duality. So we've shown that light behaves like a wave and sometimes it behaves like a particle. And so it's comfortable now, hopefully, that you can say that a photon has wave-particle duality. De Broglie came along and said, if photons can behave like both waves and particles, matter is no different. So matter should be able to behave like waves too. Weird? It's a little weird. So he said all particles will have an associated wavelength, and we can derive what that wavelength would be. So our photon momentum, if you recall from last week, or a few weeks ago, I think the photon momentum we wrote like this. So it was h over lambda. So Planck's constant over the wavelength, mass isn't involved because photons don't have mass. But if we remember from 221, momentum is mass times velocity. That's for cars and planes and whatever else. As long as you're not going higher than 10% of the speed of light, then you can use that value for momentum. So using that, we can plug in mv for your momentum. Since that applied to physical objects with matter, now you have a wavelength to describe a matter, something that has mass, So that's the de Broglie wavelength for a particle, is h over mass times velocity. All right. So the energy for these particles, you can recall kinetic energy is 1/2 mv squared, and so that is just taking the plugging in for one of the v's and the m, plugging in momentum, and then that leave a lingering v term. So they did a little algebra. Let's do the algebra because I'm confusing myself talking about it. Okay, so if we do add a v over v term, which we're allowed to do since this quantity equals 1, then we have 1/2, not v over v, excuse me, m over m. Then we've got mv, the quantity squared, over m. And mv is momentum, so I can replace that on top, and that leaves mass on the bottom. So that's a new way to write the kinetic energy of a particle in terms of its momentum. And just to give you a heads up, the book doesn't always say kinetic energy. Sometimes they just say energy. But if they're asking in relation to the de Broglie wavelength and they ask for the energy of the particle, that's the equation that they're looking for. And sometimes, very rarely, they'll remind you that they're actually asking for kinetic energy. And this slide, we won't actually use these equations, but if you're just interested, since we didn't have time this term to do relativity, if particles are moving at relativistic speeds, that means 10% of the speed of light or faster, then you have to account for special relativity in the momentum term. So that's what that's all about.
So in this energy equation, you're using momentum. Is that the photon momentum h over the wavelength?
This is for a particle. So a particle has mass, and so for momentum of a particle, momentum is just mass times velocity.
Mass times velocity in that respect.
Yeah, so you don't have to use, you only use this formulation for momentum if you're talking about a photon. Yeah.
So this all applies to particles rather than photons.
Yeah, yeah. And so at this point in time, it doesn't mean a whole lot. We're just getting the equations, but when you can actually use this stuff, you can take something that has velocity and calculate its associated wavelength. That's weird, right? So if I have mass, if I'm moving, then I can calculate my wavelength. I have a measurable, calculatable wavelength, which is weird. So we are waves, right?
So if you move fast enough, you would be transmittable by radio.
Well, you can't turn into light because your wave isn't an electromagnetic wave, but you can be wavier. Because my wavelength when I'm moving like this is really freaking small. I mean, it's not. No. It's actually really big. Is that it? Or is it really small? We're gonna calculate it.
It's non-periodic motion. How can you have a wave?
It's not your motion that dictates it. It's your whole energy. Be very zen about it, right? Your energy is vibrating, man. You're vibrating at a certain wavelength. And to get away from my hippie guy voice, if you don't have to do drugs to change your wavelength, you just have to go faster. Which maybe you want to do drugs as well, but maybe that's your homework problem. You have a homework problem where you got to calculate your wavelength and then figure out why you don't diffract when you go through the doorway.
Wait a minute. What if I want to diffract?
It would hurt. It would hurt a lot because because you have to squeeze yourself through a slit that is very much smaller than you are. So sure, black hole. Send yourself, put a slit right before the black hole. Black hole will funnel you down and you can diffract yourself through the slit. And it would hurt.
Did we just come up with physics insults? Go diffract yourself.
I like it. All right, well, that's been an hour. I don't know why I'm so concerned about it being an hour. Let's finish this conversation up real quick. What's that?
We can do the final review.
Oh, okay. Yeah, well, I think, okay, I've got a couple more slides. I just don't want to drag this on and you guys are brain dead, so. Okay, so at normal speeds, for normal ordinary objects like you and me, we're going to have a wavelength, man, why'd that, yes, 10 to the negative 31st. So really small as opposed to really large. That should be 10 to the negative 31st, or 30th. So, yeah, okay, we already talked about that, if you diffract when you walk through the doorway. So we said last couple times that when you've got a slit, in order for us to see a diffraction pattern, the slit needs to be about the same size as the wavelength of light going through it. So you'd have to have a slit that small. So that's why you can't diffract, because you can't go through a slit that small. Or you'd have to just go faster. Go fast enough, yeah. You could figure out if you were going the speed of light, what is your maximum possible wavelength? You could figure that out and figure out if there is a point where you could actually fit through a doorway.
Sounds like we'll get in trouble.
It does kind of.
So when an object goes faster, they have a smaller wave or a longer wavelength?
A smaller. Let me calculate it because I think I've confused myself enough times here. So, 6.646 is that Planck's constant? 626. 6.626 times 10 to the negative 34. And then let's say somebody weighs 65 kilograms. And then if you're going the speed of light, that's 3 times 10 to the 8th.
So just looking at the formula, you can tell that.
That makes your wavelength even smaller.
Yeah. So the bigger the velocity value, yeah, we have a smaller wave.
So that actually doesn't help at all.
So you want to go even slower.
Yeah. So if you're just standing here, you could diffract, but you're not going anywhere. I don't know. It's very strange. It's a very strange concept. So, okay. So we as people, cars, planes, whatnot, we're not going to be able to diffract big objects. But are there any particles that are small enough that they might actually fit through a slit? What do you guys think? Probably. Or it's a boring question, yeah. So electrons are extremely small. Extremely, extremely small. They're the smallest particle we've dealt with so far. So their wavelength is not so small that you couldn't create a diffraction grating that's small enough that they couldn't fit through. There's too many double negatives in that sentence. The de Broglie wavelength of an electron is big enough that you could create a slit that it could go through. That's easier without all the double negatives. Yes. All right, so this is what happens when you send electrons through the slits. You get, and this is one electron at a time. So this is, go back to Colin's question about a picture. So this is an actual picture. One electron at a time going through 2 slits. Yeah, it did the same thing. So that proves that particles act like waves. So one electron at a time, it's behaving like a wave. It's interfering with itself, and it's creating an interference pattern. Why does it say diffraction pattern? Holy cow. There we go. That's better. Okay, interference pattern. Okay, so I talked about this already. We get the pattern when one electron at a time. So you can do this experiment. They've done this experiment where you get the diffraction pattern from electrons through a double slit experiment. We learned with a double slit experiment that you can measure the wavelength of light based on where those peaks line up. And so you can do the experiment, you can measure the wavelength of the diffraction pattern created by electrons and verify this formula. So you have your predicted wavelength of an electron, you do the experiment, you get the same calculatable wavelength for an electron. So de Broglie was correct. So revisiting Heisenberg's uncertainty principle, this applies to matter as well as photons. So we can't know exactly where an individual electron will strike. We can't know exactly which slit that electron went through. If we try and see it, we'll mess up the results. So if we try and focus a light to where the electron is going through a slit, this will scatter photons off the electron, change the trajectory of the electron, messes up the experiment. So what we can do is we can just take our Heisenberg uncertainty equations and say we can reduce our slit width to a narrower slit, and then that reduces the uncertainty in where our electron is going to pass through because it's a smaller slit, so there's less options for it to go through. But if you reduce the slit width, that increases the pattern. So where it goes after it leaves the slit is going to be have a greater possibility. So by trying to find out where it was when it went through the slit, you're decreasing your knowledge about where it's going to go later on. Or basically you're decreasing your knowledge about its resultant momentum. So that Heisenberg uncertainty principle works for matter as well as waves. So, okay, so now we've learned enough stuff that we can do some problems. And you guys can take a break now and then do some problems, or you can take a break after you do some problems. What do you guys think? Okay, you can do that. Can you turn off the video, please?